And now we are going to completely and totally change gears. We're done with series. Look at that. One topic, it only took us a lecture and a half. Our next topic is complex numbers. Now, I realize I only asked you one question on the pre-quiz earlier, but almost everybody was able to find the modulus of 3 plus 4i. And I think, how many of you would describe yourselves as very confident with complex algebra? What I mean is, if I give you a complex number and I ask you to add, multiply, divide, find the modulus, you're probably going to be able to get it right, barring, careless errors. Oh, have some confidence in yourself. Okay, how many think you would get it right at least half the time? Good, that's excellent. How many of you think you have no idea how to add, multiply, subtract, or divide complex numbers? Okay, good. Talk to me later. Now, there is one key thing, the most important thing that you need to be able to do in physics is switch back and forth between Cartesian and polar notation. You have to be able to switch back between x plus iy and r e to the I theta. And if I look at this, e to the I theta is cosine theta plus I sine theta. It's probably one of the most important relations to remember for your entire physics career. You use it more than you would like. And if I just match things up, then it becomes obvious x is r cosine theta and y is r sine theta. One of the reasons this is critical is this is the foundation of one of the most important experimental tools in physics. We don't tend to talk a lot about how you do experiments in physics in our classes, but it's key. And one of the most important tools in physics is what we call a lock-in technique, where you expect the response to be at a particular frequency. The response might be very noisy, but if I lock into that frequency, then I can get a good signal. And lock-in techniques are also the basic idea behind your radio and the way it works. It picks out the frequency of the radio station you want to listen to. And so you use this idea at the heart of lock-in techniques, believe it or not. And we will maybe touch on that a little bit later on. If I continue to look at this, I can also get the formulas for r and theta. Now, this is the one notational language thing that's a little weird. So r, give me some names for r. What would you call r besides r? You're not allowed to say r. Radius. It's not a radius. It's a magnitude. Okay, we can call it the magnitude. What else would you call r? The modulus. That's a good thing to call r. Right? Because it is the modulus, right? The modulus of x plus iy is just r. It's the square root of x squared plus y squared. What else is it often called? Those are probably the two most common. There's two others that it can be called. Absolute value. That's useful to know because the Mathematica command involves the absolute value. ABS is a short. The other thing you'll hear is that it's the amplitude, right? Because it's related to wave behaviors, the amplitude of a wave. This is where I always get a little disturbed. I don't know Boaz personally. What is theta called? Angle. It's often called the angle, but that's less common once you start worrying about complex numbers. For a complex number, it has a much more most common name. Phase. And this is critical because you're most often using complex numbers to discuss phase shift. So that is going to be an essential feature. It's also called the argument. This is a little more obscure, but in Mathematica you'll see the command is arg. So that's how you find it. In Boaz, in the complex chapter section, section 4, Boaz calls it the amplitude. And to this day, I am convinced that's a typo. But I like to warn students of that because it was pointed out to me. I didn't believe it. Students were saying, oh, well, they were getting the problem wrong, basically. They were finding, I asked for the amplitude, and they were finding this, and I was marking it wrong, and they're like, well, Boaz calls it the amplitude. Ignore that. That's the only place I've ever seen it, which is why I assume it's a typo. This is the amplitude. Now, one of the key things to notice in complex numbers is when we get down to it, we are often multiplying them. And the best way to multiply them is in the polar notation because it emphasizes the idea of a phase shift. And in this class, I can guarantee you, on the final exam, you will have a question that asks you about the phase shift of some problem. Because phase shifts are absolutely central in physics, and you have to understand them, automatically. And so you can just know right now, I promise you, it will be on the final. And one of the things to get used to is, for instance, what is the complex number I in polar notation? No, that's in Cartesian notation. 0 plus I1 would be Cartesian notation. What is I in polar notation in r e to the I theta? E to the I pi over 2. So, if I multiply by I, what phase shift do I generate? A 90-degree phase shift. The phase shift of pi over 2. So one of the challenges in phase shift language you just have to be a little bit aware of is what we mean by out of phase and in phase. How many degrees are two things when they are completely out of phase? Who says 90? Oh, some of you said 90. Somebody's got to raise their hand. Who said 90? Okay, who says 180? You're both right. When we do phase interference of waves, we want out of phase to be that the two waves cancel each other. And that's a 180 out of phase because then they're 1 and minus 1. When we're doing things like lock-in techniques, we want the difference between sine theta and cosine theta. And what is the phase shift between sine and cosine? 90. So we will call this completely out of phase. And we will call going, say, from sine of theta to sine of theta plus pi, which is a factor of minus 1, out of phase. And it just depends on the application. And that's why I point this out and give you a warning. You have to know your application to know whether we're talking about 90 degrees phase shift being out of phase. Are we worried about the difference between sine and cosine? Or are we worried about two things canceling, in which case we're looking at 180 out of phase? But that language, unfortunately, does get used. Now, any questions on that? So let's go to Mathematica. Unfortunately, Mathematica and complex numbers, I think, is the one place where at some level it actually gets a little more complicated at first when you deal with variables. When you're dealing with numbers, it's all pretty straightforward. I have commands real, absolute for the modulus, arg for the angle. And so I can take 5 plus 6i, and I get the real part, which is 5. I can get the absolute value, which is 7.81023. I can get the argument, which is this arctangent. I can do the square root numerically, and it just takes the square root of each part. So notice the square root is giving me basically the first square root. And we'll talk about that later a little bit when we do more with complex numbers, right? Because you can get more than one square root, obviously. It only gives you one, so you have to be careful of that if you want the other roots. And then it can do it just symbolically, the square root of 5 plus 6i. That's not so bad. The challenge is when, oh, it's just going to repeat. The challenge is when you want to use variables. And the reason it's a challenge in Mathematica is that Mathematica assumes every variable is a complex number. How many of you have programmed in a programming language like C or BASIC or Pascal? And you've had to declare whether your variable is real or complex or integer in old versions. I don't know if you still have to in C. I haven't programmed in C forever, right? But it cares about whether something's real or an integer, and you can have to declare things. Mathematica doesn't. Mathematica just says everything's a complex number. So it doesn't know the absolute value of x plus iy any more than that it's the absolute value of x plus iy, because it doesn't know yet what x and y is. Now, notice, just a quick thing, I'm using capital I as a built-in thing to be the same as the square root of minus 1. I can also do escape, I escape, and that'll give me the funny formatted I with the double lines. Mathematica, when it does it, will convert it to the funny formatted one. You can also get what looks like a cursive I if you pick the right palette to look like an I. So in Mathematica, I need this thing called complex expand to tell it that all my variables are actually now real. So if I complex expand x plus iy, then I get what I want, the square root of x squared plus y squared. And that's really the central thing here. So a lot of, as you play with Mathematica, is going to be learning how to use complex expand. So what's one of the things that happens with complex expand? So let's suppose I want the argument. Notice it's just telling me that the argument is just the argument. And I just told you complex expand is going to treat them as both real. Why did it get upset? Well, it didn't really know whether I wanted the argument in terms of the argument and the absolute value, or whether I wanted the argument in terms of the real and the imaginary part. It has two choices. And that's where this idea of target functions come in. Right? The real and the imaginary part are the x and the y. So if I tell it, I want the argument, the angle, the theta, the phase, in terms of the real and imaginary part, it now gives me what I want, the inverse tangent of x, of y over x. This notation is this over that. So this is why I say for certain things with complex numbers, when you're dealing with functions, not numbers, but functions, Mathematica gets a little more annoying. Did that make any sense whatsoever? And trust me, you're going to have to play with it some. This also happens, unfortunately, when I go to conjugate things. If I'm using just numbers, so the complex conjugate, right? Z star is just x minus iy. The rule for complex conjugate is you let I go to minus I everywhere. That's really what the complex conjugate of a complex number is. Now again, if x and y were complex, I couldn't just do this. I also have to make sure I'm taking the complex conjugate of x and y. So I would have to write it like that. But normally, when we've explicitly put our i's in, we are assuming x and y are real numbers. That's our convention in our notation. Mathematica, isn't going to deal with that convention. So with the conjugate, on a number it works just fine. 3 plus 6i becomes 3 minus 6i. But for our function, and here I'm doing e to the I kx, notice what it did. It did e to the minus I, the conjugate of kx, because it thinks k and x are complex numbers. Okay? But I can do complex expand. And now you see Mathematica decided to get tricky on me. And when it took the complex conjugate of e to the I kx, it switched to cosine and sine form. Because it knows e to the I kx is cosine plus I sine. I didn't want that. I wanted to keep it in e to the I kx, and that's why Mathematica has a built-in command trig to exponential, but also exponential to trig if you wanted the trig instead of the exponential. So this is where I start to get into more advanced Mathematica. And I do conjugate of e to the I kx. I want a complex expand so that I have k and x real, and I want to stay as an exponential. That seems like a lot of work to get e to the minus I kx. And that's why I say this is the one example where dealing with complex numbers as functions, you do occasionally have to do more work in Mathematica than you would if you were doing it by hand for simple things. As soon as your problem becomes sufficiently complex, this doesn't change much, right? It's just applying complex expand once to whatever your expression is, trig to x once to whatever your expression is, and all the algebra is still done for you. So once you get more and more algebra, this doesn't get any harder, assuming you can type the initial expression without any typos. But for very simple things, it does look a little cumbersome. So again, that's the warning in Mathematica. That is one thing I also want to highlight with Mathematica. You're switching from a world where your errors are algebraic ones. You lose a minus sign. You forget to copy the x squared. You just write it as x. You forget a factor of 2, right? Those sort of errors you make at every step, to typos. Now the nice thing is, when you're doing a problem longhand with algebra, every single line you have a chance for making basically a typo, for copying something wrong, dropping a minus sign, and so on. In Mathematica, you basically only have a chance for a typo in the first line you type. Because if you have a typo in a command, Mathematica just chokes and tells you, I can't do that. What the hell are you trying to do? Right? Whereas if you make the mistake as you're doing all that algebra, you won't notice until the end, until you try to check it. So there is a slight advantage to Mathematica from that perspective. Now, if you want to get really fancy, and this is something you may want to go back to, I'm not going to execute these, but I'm going to show them to you. A lot of these tricks come down to the idea of how Mathematica keeps track of things in its actual root memory. And you can find that out by using the command full form. So what is e to the I kx actually? Well, it's a complex number, 0, 1, which is just I, times kx. That's what the times is telling you. And it's a power of e to that power. So the power function is telling you to take e to this product, that's what the times function is telling you, of a complex number times k times x. Notice the full form of 5x minus 6iy has a similar structure. It's ultimately addition of a product and then another product. And here the complex number is minus 6i, so you got the 0 and the minus 6. So notice all the stuff about the i's are contained in this expression, complex 0, comma something. So I have a pattern I can match. And we're going to come back to this and do this a bunch in Mathematica. Mathematica is very big on pattern matching. And it's something that you can get used to and take full advantage of. And that's our rule thing. Remember our slash dot said to execute a rule? So I can make a rule. My rule is that if I see this pattern, the Mathematica command complex and two numbers, I'm going to keep that number the same, and I'm going to multiply that number by minus 1. Notice that was my definition of complex conjugate. Find all my i's and make them negative, if I know all my variables are real. So I can trick Mathematica right? Mathematica thinks those y's and x's are complex, but it knows where all the i's are because it always has that form, complex, 0, and then some number. So I can make a rule that does the complex conjugate for me. So now, instead of using the Mathematica command, having to find this rule, I can make my life easier. If I do e to the ikx slash dot conjugate, I just get out e to the minus ikx in one step, because I've gone deeper into the Mathematica. And some of this will be a choice you make throughout this course. Right? As you see the Mathematica you use for the different problem solving, depending on how much you're into it and what you want to use it for, some of these things you'll want to do, and some you won't want to worry about yet because you're still just worrying about how to do the basic functions. But my attitude towards the Mathematica in this course, I want to make sure you all get the basic stuff down, and we'll do that. But I want to point you to the more advanced stuff for those of you interested. And that's why I encourage you to work together on Mathematica, to share files, to explore it, to play with it. Because as you go into these things, it becomes incredibly powerful. Make sense? So here's another example of where that works. If you're familiar with the idea, if I want to take the nth root of a complex number, how many, so let's say I want to take 5 plus 6i, and I want the cube root. How many cube roots are there? How many cube roots of a number are there? How many square roots of a number are there? 2. How many cube roots do you expect? If I'm dealing with complex numbers, there's 3. If I'm allowed to use the complex numbers, there's nth roots of any number. And the way this happens, right, is if I write it as r e to the I theta, what does it mean to take the nth root of that? Well, I do r to the 1 over n, and I take just the principal value, meaning I just take the obvious nth root, the positive real one. But then I've got e to the I theta over n. But keep in mind, e to the I theta equals e to the I theta plus 2 pi. Right? Because cosine and sine are periodic. So if I'm dividing this by n, I can also divide theta plus 2 pi by n. And I can do theta plus 4 pi by n. And theta plus 6 pi by n, until I repeat and get the same answer again. And I will pull out n roots. This is something you all should have done in your complex algebra classes. If you're not comfortable with this, you're going to have some homework to practice it. Talk to me on Thursday or in office hours about it. But this is a key feature of complex numbers. The trick in Mathematica to doing that turns out to be kind of cool. You just solve the equation x to the n equals whatever the complex number is you want. And you get out all the n roots as numbers. The other way to do it is to do it by hand and write it as r e to the I theta and solve it individually for each theta. And that's a little tedious and painful. If you want it not numerically, but as a symbolic representation, that's what you have to do. But if all you're interested in is the numeric roots, which is almost always all you're interested in, this gives you a quick way to do it. You would never be able to solve this equation yourself, but Mathematica gives you this cool, quick way to get all n roots. So that's a place where Mathematica really speeds up the process.
If we won't add the complex expand.
Right, then it doesn't work because you got to make sure you're telling it, you know, that you want it in the nice form with x being real. Is that true? I have to check that. This may be a case where you don't need the complex expand, and I did it just to be safe. Yep, I lied. You don't need the complex expand.
So the function of complex expand is...
Yeah, because in this case, you're just solving for the x's. It's not treating it as a variable. You're OK. So you don't need the complex expand. It's irrelevant. And that actually may be left over from an older version of Mathematica where you needed it. So I'm glad you asked that question.
So would you please explain
Complex expand? Yeah, well, what I said earlier, go back and look at it. Complex expand is what tells Mathematica that your variables are real variables, not complex ones. So you need it whenever you're doing things, usually like taking absolute values, trying to find theta, doing a conjugate, complex conjugate. Because you want Mathematica to know your x's, k's, and y's are real numbers. So go back and look at, when I post this file, go back and look at those examples, and it should be clear.
I just want to ask that, you mean for like the e to the power of I can x, the Mathematica also will think that k and e are also.
Well, e, it knows it's a number,
Okay.
right? Because I'm using capital E, that's the exponential. But notice the k and x it thinks are complex, and that's why it just writes it as conjugate there of kx. It can't actually do anything else with it.